Bien, en virtud del tiempo, vamos a invitar inmediatamente a Pierrette Prince para que presente su exposición. Adelante.
Thank you. Okay, I'm going to break the mold a little bit this afternoon and do my presentation in English. I hope everybody can understand what I'm saying. If you have any questions and you want to speak a little bit more to me about this technology, please don't hesitate to drop by our booth. It's the SGS booth. So I'm going to start with explaining to you a little bit about the theory of MMI and the actual fundamentals behind it. Now, MMI stands for mobile metal ions. It is a soil geochemical tool to help you find buried mineral deposits. Once we've gone through a little bit of the theory, and it's just going to be a very brief overview, we're going to talk a little bit about sampling protocols. Sampling protocols are extremely important for all types of geochemistries, and the MMI has very specific sampling protocols. I'm also going to explain to you a little bit about the MMI packages that are available, as well as show you a few very brief case studies. Okay. To start with, what is MMI? What are mobile metal ions? In the environment, you get a number of different forms of metals. You get the pure metals, such as copper metal. You get components or compounds, such as copper carbonate, copper sulfides. You also get metallic ions, such as the copper 2+ ion. This is the form of the ion that is free to move within the soil profile. Hence, it is termed mobile metal ion. That is the form of the metal that the MMI will actually extract. Just a very quick diagram here. If you have a buried mineral deposit, we all know that they do create a geochemical signature at surface. So what happens is, if you have oxidation happening around your mineral deposit, this will help to drive the various metals that are within the ore body to surface, and they will accumulate at surface over time. What will happen, though, with the mobile form of the ions is they have an affinity to grab onto the soil particles. They are positively or negatively charged, and therefore they will actually attach themselves and work their way into the outer coating of the soil particle. When this happens over geological time, the particles will also tend to migrate away from the source. So with MMI, the extraction is such that we will not break down the outer coating of the soil particle. So once the soil particle is encapsulated and has been dispersed away from the source, we will not be able to analyze it. The only form of the metal we will analyze is what is directly above the ore body. Hence, what you will have is you will have a very strong apical anomaly directly over top your source with an MMI type of analyses. If you're doing a conventional, such as an Acro-Regia, ICP-MS scan, you tend to break down the soil particles, hence you'll get a broader, more dispersed anomaly. Okay, some of the characteristics of an MMI anomaly is they are very sharp apical responses directly over mineralization, as you have seen. They are directly above or up dip from mineralization, and I will show you an example here of an up dip anomaly. Typically, they are commodity element responses. If you're looking for gold, you need a gold anomaly. If you're looking for copper, you want to see a copper anomaly. They do appear in soils over weathered and transported over burden, and there are very low percentage of false anomalies. They do produce higher geochemical contrasts, therefore they produce sharper and more accurately defining anomalies. This is slow. Okay, I'm going to talk a little bit about the different leaches that are available out there. I had mentioned Acro-Regia being one of the geochemical type leaches. What you have here is a graph showing a very strong digestion, and I'm sure everybody knows about fire assay. That is basically your strongest digestion for gold analyses. Now, the weaker part of the scale, you can actually put the mobile form of the ions in solution with deionized water, rainwater, and salt solutions. However, they won't stay in solution. The key here is putting the ions in solution and keeping them in solution. And it's very important to keep them in solution because being a lab person, we oftentimes see solutions become oversaturated and the metals will drop out of solution. So on the graph here, the very strong part is of the digestion chain is the fire assay. And then you're going to see a few other of the reagents that we will use in the lab, such as aqua regia, which is a combination of hydrochloric and nitric acids, Blake analyses, cyanide. It's still fairly strong and rugged type of digestion. MMI sits just above the different types of water and salt solutions. It's not a very strong digestion, but it has enough chemicals within the group of chemicals to ensure that the solutions stay in, or the elements stay in solution. So what you in turn get is, with a very strong digestion, you will get a very high background to signal ratio. Because you're putting a lot of the metals in solution, we got to deal with that. So your background levels are elevated. Hence, you get not quite of a good spatial signal-to-noise ratio. On the weaker end of the scale, you are dealing with very, very minute amount of elements that are in solution. Hence, your backgrounds and your detection limits are extremely low. When you do get an anomaly, typically you get a very strong signal-to-noise ratio, or signal-to-background ratio. Just to show you here, what we do with MMI, typically we weigh out 50 grams of the soil that you send to the lab. We mix it with 50 mils of the MMI solution. And the MMI solution is such that it will only detach the loosely adsorbed ions to the outer coating of all the various particles that you see here. Sometimes you will have copper encapsulated in with the clays. The MMI will not put these copper in solution. It'll only be the loosely bound ions that will go into solution. Just a very quick point here I want to mention. This is I will show you more details on this specific case study later on in this presentation. But this is just to highlight, it's a research study that was done in Canada, and the research group wanted to test a various number of geochemistries and see what would work in different environments. This was a VMS-style deposit in northern Ontario, buried down on average about 300 meters at depth. So what they did was they collected samples over 2 lines, and this is one of the lines here, and they collected the soils, submitted them to the various laboratories, and they did an aqua regia, they did an enzyme leach, they did an MMI, hydroxylamine leach, and a water leach. And what it turned out was that this is the actual up-dip projection of the mineralization. It's mostly lead-zinc mineralization, but there was some gold, silver, and some other base metals. MMI was the only technique that identified the mineralization. This is straight out of the report, the Camiro report, and it is just zinc. I will show you more of the elements and the associations later on. However, the reason this is working so well for MMI is the background levels in that camp are extremely low, and a lot of the other techniques are not able to distinguish between the backgrounds and the actual anomalous values. With the MMI being very low and having very low amount of salts in solution, we're able to distinguish the background to the anomaly. And this is the other line. I mentioned they had done 2 lines. This is the other line. This is the up-dip projection of the mineralization. All of the other geochemistries are flat, and this is the MMI with the zinc. We did have a little bit of an anomaly at the very far end of the line here. The client had a look at the data. They went back, they repeated the MMI to see if they were able to repeat this anomaly. They did repeat the anomaly. They then drill tested it, and they actually discovered at about 650 meters at depth, it was the actual structure that had folded, and some of the ions had come up through a fault. So, MMI is a non-selective multi-ligand extraction. It will detach the metals irrespective of the substrate. It is based on complexing with strong ligands, and it is also based on minimal attack of the substrate. It does make it energetically more favorable for the weakly attached metals to be in solution, and therefore it will minimize potential for reabsorption. It will also minimize intermetal competition. There are enough ligands within the solutions to keep all of the metals in solution. So what are ligands? Ligands are strong complexing agents, and they are specific to certain ionic species. They can either be organic or inorganic chemicals. They do alter the solution chemistry of the target species, much as the same effect that cyanide has on gold. They can be used to desorb or detach, and they are also used to ensure species remain in solution during analyses. I'm going to show you a little bit more about this Camaro research study on this Cross Lake deposit in northern Ontario. A little bit of history here on the deposit. It is a VMS, base metals. They did the two lines, line 40 and line 6 I had mentioned. And overburden was about 30 to 50 meters, and the water table was about 2 meters to a little greater than 1.5 on line 6. Okay, so here's going back to one of the lines here, line 6. This is the up-dip projection of the mineralization. This is just the stacked bar charts for the base metals. Here is your zinc and your cadmium. Note cadmium is very important with zinc. It's a partner to sphalerite. If you don't have cadmium, be wary whether it's a sulfide or not. So there's your base metals on this line, and your precious metals on the same line. Here's the up-dip projection. Remember I had mentioned that this is a VMS-style deposit. This is very indicative of a VMS-style deposit. It's all got to do with zonation in the ore body. We see this on every VMS-style deposits that we work on. The precious metals are sitting on one side or the other of the deposit. Very indicative. So what you're looking at here is some gold and some silver, a little bit of cobalt nickel. Cobalt nickel are very good lithological elements. Okay, and here's the second line, line 40, the base metals. Here again, your up-dip projection and your base metal anomaly. Here they had a very strong copper response, and it was a known subcropping of diabase dike, so they picked that up. No surprise. And here's the up-dip projection on this line. Here's a little bit of a precious metal anomaly. It's not very strong. Here you're down to about 270 meters at mineralization. Gold is not so strong, but they did pick a little sniff. And I just wanted to very quickly show you the two different types of soils on these lines. One is a podzol soil, and typically what they did in this area, you see there's a heavy organic layer. They actually collected the MMI down to about 10 centimeters below the living organics. They're pretty much just within that leach zone there. The next line was the Luvasol, not very well defined, more clay-like structure. But here again, what they did was they collected the sample just about 10 centimeters below this arbitrary line that they figured was mostly organic. So they just went below the organics, collected their sample, and that's where the MMI was sampled. So field sampling procedures, you need to collect MMI at a consistent depth. It's not rocket science. You don't have to go looking for various specific horizons. MMI is a depth type of geochemistry. It's an interface sampling technique. In areas where you have organic cover, what you need to do is identify where your organics begin to decompose. Once you identify where they begin to decompose, you measure down 10 centimeters, and then you take that next 15 centimeter plug. If you have no organics, it's easy. Your interface is the soil to air, and all you do is you go down 10 centimeters and you take the next 15 centimeter plug. However, stating all of this is the recommended procedures. We do recommend orientation surveys. They're valuable in doing before you start any large geochemistry program. They will help you identify whether this technique you will use will work for you in your area. They will also help you identify the proper sampling protocols as well as sample spacings. I'm trying to rush here. MMI extractants, we used to have very small packages. One was for base metals, one was for precious metals. Over the years with the developments, we now have been able to put all of the elements into one package, so it's more economical, of course. And the package is called MMI-M. There's over 54 elements in this package. Of course, you don't have to choose them all if you don't want. You can choose subsets. However, they are very important. There's a lot of lithological elements within this package that will help you do some mapping as well. The other package is MMI-ME. It's the same digestion as this, and you will get all these elements. The only difference is you have lower detections of chrome. If you're doing kimberlite exploration or if you're exploring for nickel sulfides, very low level chrome is important. And as well, vanadium we can get in this package, and vanadium is very useful for uranium exploration. Other elements that can be added onto the package are selenium, sulfur, bromine, iodine, lead isotopes, very important. And that's just a pictorial of all of the various elements. I'm moving. Just to finish off here, I just wanted to show you the one case study here that I have out of Argentina. It was done many, many years ago, probably about 1996 or 97. I was very new on the scene at that point. However, it was done over San Jorge, and you probably know San Jorge more than I do, but it has a various number of what I might call geological domains or zonations. It's a porphyry, and most porphyries are very similar to this. You have a leach cap, you have an oxide zone, a primary zone, and an enriched zone, and your primary zone. And what's interesting about this, with the MMI, it was a no-brainer. The copper was screaming, had a very, very nice anomaly directly over top the porphyry. However, the copper was so strong, it was actually diluting the rest of the elements and what the rest of the elements could tell you. So what they did was they removed the copper from this graph and they used the other elements. And what you start to see is the zonation that appears in this deposit. Flanking the actual porphyry, you have your zinc, your cadmium, and your lead. The center core has your gold and your silver as well as your copper. So there's a lot to be had with a lot of the elements that are part of the MMIM package. That's it. Thank you. I made my